Okay, thank you everyone for joining us today for this session of the NOAA Innovators series. I'm going to pass things over to Tiffany House.
Thank you, Erin. Hello, everyone, and thanks for joining us today. My name is Tiffany House, and I am the Commercialization Specialist for the Small Business Innovation Research Program for NOAA. This program offers competition-based awards to encourage technology innovation among for-profit small businesses to engage in federal research and development in agency mission-related areas that has commercial potential. Today, you will hear from Dr. Chao of Remote Sensing Solutions. Dr. Chao will tell us about his latest technology and how he has benefited from the NOAA SBIR program. Dr. Chao is the principal investigator of this NOAA SBIR Phase 2 effort. He has been with Remote Sensing Solutions since 2012 after working at NASA Jet Propulsion Laboratory. Dr. Chao contributed to the first NASA satellite to measure ocean salinity from space. He has a Ph.D. degree from Princeton University and has more than 100 peer-reviewed publications. Ladies and gentlemen, it is my pleasure to introduce you to Dr. Chao.
Thank you. Thank you, Tiffany. Can you see my slides okay?
We see your slides great, thank you.
Okay, great. Thank you, Tiffany, for that kind introduction, and thank you to your office, SBR office, for your help and then support throughout the last couple of years. I'm going to give you a brief progress update on the Phase 2 project is ongoing. Focus on Lake Erie modeling and data assimilation to improve operational forecast. I want to thank my colleagues and Carrie and Zhang at Remote Sensing Solutions for doing most of the computational analysis. And also want to thank my co-investigators at Atmospheric and the Environmental Research in Boston, AER, another company has been doing atmospheric and ocean research. Thomas, Mark, and Rui Ponte has been instrumental getting this project and partnership started and are working with us throughout the last couple of years. I want to also acknowledge Dr. Philip Chu and Eric Anderson at NOAA Great Lakes Environmental Research Lab for technical contact, technical support, and then the feedback for our project throughout the lifetime of this effort. And then two collaborators, Professor Chang-Sheng Chen at the UMass Dartmouth, providing support on FVCOM. We learned at the start of this project, and also Professor C.K. Sham and his postdoc, Dr. Jia at Ohio State University, contribute some of the satellite altimetry activity. So before I get to the ocean forecast, I just want to start with the background is really looking at the NOAA weather forecast at the model to guide us to work on operational oceanography. Usually before I visit my colleagues in Michigan, and the first thing I did is looking my smartphones and try to look the weather conditions, what type of temperature they have, whether they're gonna rain, what kind of coat I'm gonna bring. So it's really be part of my decision making when I make travel plans. So we took that for granted. It's available on the fingertip. It's only emerging in the last couple years, and then whenever you go in the globe, you can find a real-time weather prediction in the next few days. So in my mind, this is one of the most successful examples of applied science and technology for societal applications, and then people like me and anybody in the community benefit from the observation, from the modeling prediction, and then the interface provide this information on our fingertip. It sounds pretty easy. You go to your smartphone, you type your zip code, and then information come out. And then I did a little bit of research behind this black magic, and there's a lot of infrastructure behind it. So if, according to my quick summary, of this activity, the weather forecast. It involved a number of different institutions and then groups and scientists and companies. It's a true partnership between the government, academic institutions, and private industry. Just based on my brief survey, starting from observing systems, the weather station, the National Weather Service, and have a network of regional weather stations. They collect measurements, they launch balloons every 12 hours. NOAA and NASDS launch a number of different weather satellites and then provide information near real time. And that information go into this gigantic weather forecasting models running at National Center of Environmental Prediction, NCEP, in Washington. And that's give the North America and the global weather prediction, the map I show on the middle lower panel. And all the way to, I did a brief survey, there's almost more than 200 companies around the country take this NOAA information, provide so-called these last mile services, and then provide information to the user like you and me. That's account to multi-billion-dollar private industry like weather.com. You open your newspaper, look at the weather prediction, AccuWeather, you look at the TV report. So this company play an integrated important role in this entire supply chain, and then from observing the weather to forecast the weather conditions, and all the way to provide the right customized information and available on your fingertip. So that's a quick background and thinking about operational oceanography. As many of you are aware, we are probably at least 1 or 2 decades behind the weather forecast in terms of the operational ocean prediction. Is still in infancy. Starting Great Lakes actually leading many of the regional coastal areas to do ocean water forecasting. Dr. David Swart started the Great Lake forecasting more than a decade, and starting the first model back in 2006 in collaboration with professors at Ohio State University, developed the first Great Lake forecasting model system, and then starting with the Princeton ocean model, eventually transitioned to the finite volume coastal ocean model we call the FVCOM, which is the model is operating today. Great Lake observing system come along as an integrated part of this IU's integrated ocean observing system. There's 11 of these different regions around the country. Great Lake observing system is one of these 11 networks in the region to provide real-time observational data, model forecast, as well as user-driven products, and then to help people like you and me make better decisions in our daily lives. So the Great Lake today, before I started projects, you can access information 2 different ways to to make decisions. You can take the observation, and you can try to use that data to make decisions. There are limitations, as you're aware, for the observational-based decision making. You only have limited number of parameters. Whatever the station measure those parameters is limited in spatial coverage, where you only have information at that specific location. And then observation doesn't really provide you the forecast information. So that's bringing in the needs of the numerical models. You bring computational models into the play. You can use the data to validate your model. You start with either Princeton Ocean model or FVCOM. You can simulate. This is a particular lake, Erie's animation in the bottom. And then you can evaluate on how realistic the model is, and then you can use the model to derive a number of different products, and that's where guide your decision making. So that's the kind of the state of art decision making process within the Great Lakes forecasting systems. So we bring to the table is try to integrate the observation and then data into a, through a systematic way of we call it data assimilation, so that we not only bring the data to evaluate the models, but also we bring the observational data to influence the model, to improve the model simulation. The model is only a digital interpretation of the reality. There's a deficiencies of model physics, model formulation. There's approximate assumptions with the model. So observation will help us to improve a number of deficiencies of the model. So integrate observational data and models through the data simulation, and then provide the forecast, and that should provide a better guidance for decision making, very similar to the atmospheric community has been doing to integrate the data with the models and then provide the forecasting guidance. So that's bringing to the core of these projects. We introduced data assimilation into the Great Lake operational forecasting system. Before I get to the specifics, I just briefly describe the process of data assimilation. What I've shown here is think about a particular variable as a function of time. We try to use the model to simulate the truth, which is the green line, which is the blue line. We don't really know. And then we collect data in the blue stars, and then periodically, it could be tide gauge stations, could be a buoy measure the surface temperature, could be a particular mobile platform like a gliders measure the profiles of the temperature in the lake. So we collect those discrete data in the blue stars, and then we try to use the model to approximate the truth, so we can simulate not only those data location, but also simulate the lake condition everywhere. So as you know, model is only approximation of the reality. So you can see there's a difference between the green lines and then the blue lines. So when you collect the data at that particular blue star location, you can see the discrepancy between the observed data and then the model. So the question is, how do you use the data to improve your model initial conditions so that the future forecast will become a little bit more closer to reality? So in this particular schematic, I showed you the kind of incremental data simulation methodology. So you can stop the model every day or something and then compare with the data, and then use the data to combine with the model estimate and come up with a better analysis. And that's the red square is, and then you initialize the model with the analysis that hopefully give you a better forecast for the next day. And then you repeat this every day or so, and then hopefully in the not too distant future, your model forecast will be closer to the reality. So the data simulation is all about how do you combine the observational data and the model forecast at the first guess together, so that you can you have a better analysis closer to the truth. So it's about a weighting function between the observational data and the model forecast first guess. So it's data simulation is all about how to select this the weighting function between the two. So that's the 101 data simulation. There are many different methodologies you can adopt. You can simulate data in the empirical way. You can put the data, replace the model, so you make the model perfect at that particular location. Or you can nudge the model closer to the observation, giving some kind of weighting function within some time constant or something. So that's basically costs no computational overhead. But as you can imagine, as soon you stop putting the data, start forecasting, the model will drift away. That's have its own limitations. And you can do optimal interpolation, use the data to influence not only that particular location, but also nearby locations, and using some kind of empirical distance. We call it influence radius. Say depends on the characteristic spatial scales in the lake. You can say this data influence anything nearby within 10 kilometers or 5 kilometers, and you can put a weighting function. The further away from the data location, the less influence it can be. So you can define this empirical influence of the data, and then there's essentially no computational, very little computational overhead, but the dynamically have very limitation. You don't really benefit from all some of the dynamic information and knowledge the model can provide. So one has been using as computer become available, more and more computational powers, the community has been moving on to dynamic data simulation, either using three-dimensional methods or four-dimensional methods, or use multi-ensemble members and then to perturb your models and then make multiple forecasts. So the major decision to select the 3D VAR for our particular implementation is mostly due to the computational overhead. So both the four-dimensional variational methods and ensemble methods require many times, usually 10 to 100 times the model runtime, where the 3D VAR only increase slightly of the computational, usually no more than 2 times the model simulation. So that's another constraint when we select the data assimilation methods. It's a computational overhead for real-time operational forecast, because the model has to be run faster than real-time in order to provide the guidance for the future. So that's our rationale to select the 3D VAR data simulation. Just one more slide on the principle of the data 3D VAR. The way we assimilate data through 3D VAR is to define the cost function. The cost function, you can think about a simple RMS difference between the model and the data. The way 3D VAR works is to minimize the cost function, to ask the question, what does it take to make adjustment of the initial guess to give you the minimum misfit between the data and the model? So in other words, if you put a delta correction on your first guess, your analysis will be much closer to observation, give you the minimum misfit between the data and model. And then you use that analysis to initialize the model and then to initiate the multi-day forecast. And that's forecast supposed to be closer to a reality as your future. So you can repeat this process every day, every interval for your region of interest. And then your analysis should be closer to reality than the model forecast. So that's kind of the data simulation procedure we have been adopting. We have been tested 3D VAR data simulation in several coastal environments, has been extremely effective. There are multiple papers published in the last decade or so apply the 3D VAR data simulation in both California coastal ocean as well as Alaska area, Prince William Sound. We have been doing fairly extensive implementation and validation efforts. And there's multiple papers and then documenting the 3D VAR methodology, as well as the implementation and the validation during the field campaign, engaging real-time observing system, and then validate the performance of the models and the impact of the 3D VAR data simulation. So feel free to contact me if you're interested to look into details of these studies, and I'm happy to share some of those PDF papers and then talk to you offline. Back to the Lake Erie observing system. So we decided to pick 2005 as our baseline to do a hand cast study before we proceed with operational forecast. There is a lot of advantages to do a hand cast in 2005, simply because this is a year have enhanced observing system implemented for the Lake Erie. We picked Lake Erie to start simply because the size is relatively small, computational overhead is small, easy to repeat many experiments. And also 2005 have multi satellites available, provide sea level altimetry, sea level measurements, along with multi-moorings, provide vertical profiles of the temperature in the lake. What I've shown here also, there's a number of the tide gauge stations, both from the US side measured by 2-digit numbers. The Canadian tide gauge stations are labeled by 3-digit numbers. They provide the water level measurements real time. Some of the orange dot in the middle of the lake, those are the temperature strings, and then instrumented from the surface to the bottom of the lake, give you a profiles once the instruments being recovered. So this is one of the most comprehensive measurements being deployed in the last 20 years or so. So there are 4 satellites, a different color representing the overpass of the satellite from JSON altimetry satellite, GeoSat follow-on, GFO, Topex Poseidon satellite still working. The NVSat from European Space Agency also is operating. Thanks for the Professor C.K. Zhang and then his postdoc, Dr. Chao, provide a lot of the data processing from the altimetry satellites. If you want to know more about altimetry satellite, and then get in touch with me, I'm happy to talk to you more. There's a report from Ohio State University processing data all the way back to the 80s, have multi-decades records data being processed. So the first validation for the model and the impact of the data simulation is shown in the temperature maps. What's shown on the left-hand side is the satellite observation aggregated August 2005. Total only 76,000 of data point over this particular month. When the cloud is not many clouds contamination, you can see the lake temperature really well from the AVIRCHAR satellite data. The color bar shown on the bottom. The upper right panel showing the FVCOM, the model simulation with that before we assimilate data. So clearly you can see the simulation is too warm, so-called a warm bias on the lake, and also lack of the model showing multi-degrees. I included some of the data statistic here. If you look at the bias between the model and then the data, you see almost more than half a degree bias, and the RMS is approaching 1 degree. If you average the entire lake, it's highly correlated. So the model does capture the spatial variability of the lake temperature. When we start assimilating satellite data, so the bottom right panel showing the RMS difference between analysis after the data simulation with the data. It's not the independent validation because the data we use to compute is already being assimilated into the model. So it's a consistent check of the system. Clearly, you see the warm bias is being significantly reduced from 0.7 degrees to 0.2 degrees. And RMS also cut in half from 1 degree to about ½ degree, still maintaining a high correlation in space between the data and the model. So this is a well-known problem for the lake operational lake forecasting system. So we were able to use a dynamic data simulation method to reduce this model bias. There has been study in the past and try to use the satellite data to do the nudging and optimal interpolation, but the 3D VAR methodology seems to be very effective to correct this warm bias and using the model dynamics to spread out the observation data sets. Another way to evaluate the impact of data simulation is to use independent data. So in this graph, we compare the model and then also the data simulation analysis. We call it DA analysis. There are 2 data simulation. One is to assimilate SST only, that's purple lines, and then the green lines assimilate both the SST and then the water level from the tide gauge and then satellite altimetry data. So there's apologize for the multiple lines. It's messy here. It's hard to see. In terms of the observation on the top, you see a seasonal cycle. Clearly, all the models and reproduce the seasonal cycle. There are subtle differences. So the bottom panel, I do the model data differences. In other words, if you see the no data simulation case, crayon lines on the bottom, so you see the bias, the discrepancy of the model is one bias in general, but you see this one bias different from the season, from month to month. As you assimilate SST data, as I shown earlier, you'll bring down the RMS differences from the crayon line to the purple line, so you reduce the SST error. But that's not the independent data set. So if you assimilate all the satellite data as well, SST plus the water level, using the independent data, you can see the green line, you see dramatic reductions of the green RMS difference by the green line. So this is the independent data, the T12 data from the temperature vertical profiles is withheld as an independent data set. So we are able to independently validate the relative impact of satellite SST satellite data, as well as the other data sets from altimetry, water level measurements, as well as tide gauges. So that's assuring to see the water level data simulation have a significant impact, not only improve the heat storage, but also the surface temperature as well. I believe this is the first time we bring in the water level satellite data simulation into the Great Lake water operational forecasting system. So that's really a significant milestone from us to really making a fundamental improvement of the forecasting system. I will go quickly for a couple of these messy time series again, focus on the water level. As we simulate satellite altimetry, water level measurements, as well as the tide gauge system, we are improving the tide gauge water level this forecast as well. So the top panel showing the raw time series, the bottom panel showing the difference. Simulation minus observation, just focus on different colors. The crayon is just a forwards model without any data. You have a lot of places you can see this significant model RMS with the data could be as high as many 5 to 10 centimeters. So as you assimilating satellite data, as well as the temperature data and other tide gauge information as well, and you were able to reduce significantly the water level at the tide gauge location. So this around the lake, and then the water level getting much more realistic by assimilating temperature data in the middle of the lake. So that's kind of interesting, see how dynamically we can propagate the observational data into other places. So you can see the crayon RMS difference get reduced in purple when you assimilate the satellite altimetry as the tide gauge data, as well as you bring SST data and then into the data simulation, you improve the water level as well. One more illustration, not only on the around the lake water level get improved, the water level in the middle of the lake also get improved as well. We have very little information, only a few of these locations. We were able to calculate the dynamic height using the temperature profiles measurement on these three different buoy locations, and then you can see the compare against the satellite data, which is only available periodically, showing the red dots here, and then you can see the data simulation in green. Seems to agree with satellite observation much better than no data simulation. So, so that certainly gives us a confidence of our data simulation. We're improving water level simulation everywhere, not only around the lake, but also in the middle of the lake as well. A couple of slides on the vertical impact of the vertical profiles, and this is one particular location in the middle of the lake. The top panel showing the depths versus time. This is the summer season from April to November, when we start to deploy the buoys after the winter time, somewhere in the spring, April, May timeframe. So the top panel showing how the evolve the seasonal cycle as summer come in. You can see this mixed layer again pushing deeper and mixes deeper as you go to the fall season. The model itself, before the simulation, the middle panel showing today's operational version of the forecasting system without data simulation. So you can see clearly the deficiencies of the vertical extent of these mixed layers. The model is not penetrate deep enough, not quick enough. So if you do the model data difference and showing the bottom panel, so you can see relatively small warm bias in the middle, but really the discrepancy in the subsurface about 10-15 meters. So you can see the discrepancy of the temperature of the subsurface can be as high as 5 or even more degrees C. So that's really the major deficiency of the current operating system is the lack of this penetration of the mixed layers, and then due to a number of different model formulation, could be the turbulence closure scheme, could be atmospheric forcing. A number of factors contribute these discrepancies. So, well, the expert to develop better models, better atmospheric forcing, I think ocean data simulation provide a quick adjustment of the model simulation, so we can provide a better forecast without waiting for the model to get better. So what I'm showing here is the same similar plot on a different location. This is another part of the lake showing the same way. The top panel is the data, the middle panel showing the model simulation, and then the bottom panel showing the difference. In this particular part of the lake is apparently have a different dynamics control of the subsurface. In this case, the model subsurface is too warm. So in other words, the model give you too warm a temperature in the deeper part of the lake. So you can see below 30 meters, the model is more than 5 degrees too warm. So that's kind of another interesting feature. It's not the simple fix of the model when one region, because the model dynamics is very unique from one area to the next. So that's kind of the justification for doing dynamic data simulation. So this is again the two different locations, and then the left panel showing one location, the right panel showing the second location I described earlier. What I try to draw your attention is just the three different panels. The top panel showing the impact of the data simulation. It's the RMS difference of the model. So you see the deficiency of the current operational system used today is very cold in subsurface in left part of the lake, and then it's warm in the right part of the lake. The middle panel show you is a data simulation of all the information except this particular location. So we try to withhold this data for independent validation. So you can see the data simulation reduce the differences somewhat, but still there's a still significant difference between the model and the data. The bottom panel show you assimilate all the data, including this particular information on this spot. So we are not really validating independently in the bottom panel, but just to demonstrate how realistic we can make if we have a sufficient amount of data in different part of the lake, and then how much improvement we can make for the entire three-dimensional condition. So so as we have more and more increasing more number of the data, so we can start to bring more data nearby. Currently, we only have a finite number of data sets. If we host the data, then the impact of data simulation is very limited. So that's another point I want to make is to try to increase the number of observations as we move along. Just to summarize what we have been achieved over the past year of this phase 2 effort, we demonstrated that 3D VAR data simulation is very effective to improve the model initial conditions, to improve the model forecast, specifically reduce the warm bias significantly, assimilating both the satellite data and the in situ buoy data. Water level simulation is also improved, both by around the lake and then also in the middle of the lake. And we can improve the subsurface temperature, which is one of the major driver of bringing satellite water level simulation into the operation forecasting system. So we can improve the entire 3-dimensional temperature conditions, and then in order to get a better forecast. There's a couple of things ongoing. We are year 2 of the 2-year phase 2 projects. We have ongoing exercise to repeat the same handcast of 2005 with 2019. We demonstrate real time running our 3D VAR operational system in parallel to the NOAA Great Lake Laboratory, running the same model, exactly the same setting, except no data simulation. So that way we can run an independent and parallel comparison by the end of the year, and hopefully before the end of the project, to demonstrate a real time. We can do this 3D VAR data simulation in real time, and then demonstrate the impact of the data simulation. We have a parallel effort exploring alternative data simulation methodology, particularly by the Atmospheric Environmental Research Group in Boston, our co-investigator there, and looking for ensemble methodology to adopt so-called the DART software developed at NCAR. Is the ensemble data simulation methodology developed at NCAR, implemented with the FVCOM system. So we can do a parallel assessment on the 3D VAR versus ensembles data simulation, both in terms of the performance and the computation. Clearly, ensemble methodology is more expensive than 3D VAR, but we want to evaluate the performance and then keep in mind the computational cost will be a little bit more. We did do a research on the 4D VAR methodology. We decided not to get into that direction in this project, simply because in order to do a 4D VAR, you need an adjoint model. I think FVCOM adjoint model has been activities developing the adjoint model for the FVCOM, but it's not mature for us to adopt at the start of the project. A couple of the new directions: we want to transition research to operation, a well-known R2O problem. Hopefully by the end of the project, we're transfer the code we developed as well as knowledge to NOAA, so that they can implement into their operational forecasting system. And then working with the SBR office and their teams, we like to find a number of different use cases and then find the practical applications, and then to really thinking about the business model, maybe after the success of weather forecast enterprise, and learn something about how to develop a viable business model for the operational ocean prediction. There's a couple of wish lists and feedback to the NOAA observing systems. Clearly, we need more data, as any modeler and the data simulation people will tell you. Specifically, we need more subsurface data. We have quite a bit of surface measurements for surface temperature, water levels. Periodically, we have a few buoys measure the subsurface data. So that's clearly one of the first information I would propose, the observing system to collect more subsurface data. And there has been an effort to install a high frequency radar at some of the Great Lake locations where the velocity is relatively strong, so they can pick up much more a good signal from the freshwater lakes. So hopefully have more velocity data for us to not only validate the model, but also building into our simulation system. So having velocity data is critical. There has been some drifter deployment in the past, and hopefully that will be more routine. Deploying drifters provide velocity information. That's another thing, depends on the use case. Some customers may want the velocity information or something derived from velocity, like trajectories and dispersions, particularly for biological ecosystem applications. Velocity is the key. So having a better prediction of the velocity is critically important. So that's what I prepared so far, and thank you again for your attention. Be happy to answer the questions you may have.
Okay, thank you, Dr. Chao, so much for that presentation. I'm bringing myself and Tiffany back online now for the final portion of the webinar. We do have a couple of online questions. Tiffany, also feel free to jump in at any point, but I'm just going to start. Someone asked, very interesting FVCOM bias / RMS / core graphics. I was curious what software produced those, and if by chance the data operated on to produce those resides on a cloud environment or a NOAA cloud environment?
It's a good question. We are in the middle of our projects. We, I guess earlier questions, some of the graphic, this is just our MATLAB programs, and then developed on our server. We are doing our computation on our local cluster computers. I think NOAA doing their FVCOM simulation on their computer. I don't think it's on the cloud. My team have some experience running a model on the cloud, not FVCOM, is more on the ROMS model, California Coastal Forecasting System using ROMS. So we did implement ROMS model on the cloud.
Where it was late.
I'm sorry?
Oh, I'm sorry.
Okay, so we did it on the clouds. We have some experience. I think it's straightforward to implement what we did on the clouds. I think it's a great idea to do the computation on the clouds and also do this diagnostic on the cloud, so people can directly access the information we produce and share with the broader public or researchers. And then currently sharing this data and then graphics is a little more challenging, is probably case by case. But if you have specific interest, and just drop me an email, be happy to send you graphics and even data. And I think I need to talk to Phillips and Eric Anderson at the Great Lake Environmental Research Lab. Assume they're okay sharing information with other people.
Okay, great. And that person also just wanted you to know that they use MATLAB, and that they think working together on the cloud makes for a great collaborative space. So they may be getting in touch with you.
I think the future to collaborate on the cloud, and then I think in the longer run will be cheaper running on the clouds. And then I think when I did my investigation about a year or two ago, running big model like 3D ocean model on the cloud, the running is not that expensive, but storing the gigabytes of data and also bring the satellite data real time into the cloud is quite expensive operation. Bring in and out the cloud costs money. So maybe as cloud getting more popular, the cost will be reduced, and I need to revisit that now.
Okay, great point. And we do have a couple more questions here online. So someone else wanted to know, have you used VIRS SST data and compared to AV-HRR accuracy?
That's a good question. We look at that data because we did a handcast back then. There's, we have to go work with old data sets. For the real time, we are not bringing the VIRS data, but potentially that will be additional, maybe even higher resolution to help us. But the AVHR data is in the summer season, there's a tremendous amount of data already. So I would imagine would be helpful, may not be fundamentally change what we are doing. I think it will be a valuable data to have.
Okay, great. Thank you for that. And then the last online question we have for right now is that someone wanted to know, are the DA results from the analysis window or from a forecast run?
Well, the DA is for the analysis. So if you basically what I shown you is basically a forecast. If I say no data simulation, would be the forecast showing here, the initial guess, and then the analysis is after data simulation. Did that answer the question?
Okay, great. Yeah, it looks like that was a good answer. So we did have another question that came in from someone who would like to know, they said it's a very interesting presentation. Do you think it would be possible to assimilate SSH data set to further improve forecasting accuracy?
Yeah, that's a good question. We focus on validating the handcast at this point. I would imagine the forecast will be improved. I think the key question is how much that improvement will sustain with our time. So in other words, how quickly the model, the new forecast will go back to the unassimilated results. So that's the question is to be assessed. At this point, we primarily focus on the improve the initial condition of the analysis, and that could be the next paper we'll work on is focus on the forecast assessment. I'm sure the NOAA scientists and the Great Lake Lab, they are interested that answer that question. If people in the audience have specific interest, we'll be happy to hear from you and then collaborate. And if someone have a students or postdoc interested, and we're open to provide we have all the forecasts available. So it could be a good intern project or student term papers to do that kind of assessment. And there should be a material to write a paper, but we're just busy. We focus on analysis at this point.
Okay, great. It looks like that's all the online questions we have for the moment. So Tiffany, did you have any final words?
No, I just want to say thank you to Dr. Chao for doing this presentation, and I hope that you get a lot of good feedback and someone possibly collaborating with you. And thank you, Erin, for running this webinar.
Okay, you're very welcome. So yeah, I'm not seeing any more questions. I think we'll just leave it there for now. So thank you, everyone.
Thank you, Erin, for your help. Thanks, Tiffany, and your team for your support.
Okay, thank you. Have a great day.